Okay, so let's see what we have in store for us this week. We've got a couple labs. I think they should be very easy. And we have an in-class assignment working with sequence diagrams and turning them into code. And that so that would be presented on Wednesday, and those are due Thursday evening. And then at this point, I'm thinking of doing another in-class assignment that would be due at the end of class, kind of a self-check on how you're doing and where you are, doing an old midterm, open book, with able to work with other students and so forth, but strictly in class. So if you aren't in class on Friday, you are not going to get credit for that. So that's what I have in store for you. There's an outside chance I may do something with A15 on Friday, but at the moment I'm thinking I'll roll right into A16. Any questions about anything? Then let's go ahead and plow forward. So, characters. I can assign a character to CH. I can print it out. And there should be no surprises. The letter A is printed out. What is, not intended to be a trick question, but what internally are characters stored as in the computer generally? Hexadecimal, all right. Yeah, I would be even more generic and just say a number, right? All right, so we can actually show that. I can create an integer called as, well, let me see, ch as num, and I can say that ch as num, and I can assign the letter A to that. But when we go to print it out, it'll print it out as a number. So let me modify this code here. Print it out as ch, assign A to this integer, print that out. It'll compile just fine, and when we run it, so in fact, a character as created on line 7 really is just a small number. And the only thing that's different between ch and ch as num, other than the size, the integer on line 9 can hold tremendously large numbers. The character on line 7 will only hold numbers up to 200. There are only 256 values that can be stored in ch. But the only difference, other than the size, the only difference between them is how they're displayed. So the computer runs some sort of algorithm there on line 11 and determines that 65 should be, that internal representation in the computer of 65 should be represented as that glyph that we know as the letter uppercase A. And the algorithm that it runs on line 12 is to take that same numeric representation and represent it as a 6 and a 5 that prints out, right? So that's all that's different other than the size. The only thing that's different between them is that algorithm that runs for what it should actually spit out and show us. Let's dig down a little bit deeper in it being represented as a number. So what do I want to say here? And I imagine you all have had this in the past, but I like to reprise it just a little bit. For whatever reason, this seems a little bit alien, but actually it's quite identical to how we deal with things in our own number system. So in our own number system, we have a decimal system, which just simply means we have 10 different glyphs that we can use to represent a number, to represent a digit. And so I can make this a 3, that's a 0, this is an 8, and this is a 2, right? I just pick one of those 10 glyphs for each of those positions. And then 10 to the 3, that of course is 1,000, this is 100, this is 10, this is 1, and all we have to do is multiply the value of the glyph times that position. So we end up with 3,000, 0, right, because 0 times 100 is a 0, obviously, and 80, and 2. And then we add them all together, 3082. So that's so intuitive that it's embarrassing to show, but the exact same process occurs here. If I have that one, and that one, and that one, then I could say that I could look at all these, but these are just leading zeros, so we ignore them. Starting, I guess we should write what these are. So I would say 1 times 8 is 8, 1 times 4 is 4, 1 times 1 is 1. I guess we have a 0 in there. And we add them all together and we end up with 13. So the process is exactly the same regardless of the number system. The only, I guess, a big difference is whereas in our system we have 10 different glyphs to choose from, in this system we only have 2 glyphs to choose from. In our case, we assigned them the glyphs 0 and 1 for obvious reasons. So what about this program then? Let me run it one more time. A is 65. So how do we, let me change this up. What bits get thrown for 65? 64 and 1. So what's a generic algorithm or a generic process that I can use to get the correct bits flipped on that? How did you know it was 64?
Take 65 and then subtract the biggest number you can.
All right, so that's the key, right? You basically go from the highest number down available. These are all the positions that are available to us. And let's look at it with 3082. I suppose I could this would be 10 to the 4, which is 10,000. Kind of think what I'm going to do is just do that. And so we would pick the largest. We have 3082. We basically find the largest position that's under 3082, and that would be 1000. So we go ahead and get 3 of those, subtract it, and then we have left 82. We find the next position. 100 is larger than 82, so we keep going down. We find this, we get 8 of those, and so forth, right? So that's a process. So yeah, those two bits are for the uppercase A. What does intuition tell you that the lowercase a would be? I mean, does that not seem intuitive?
Either up or down. 65
Oh yeah, I suppose I could subtract 26. But let's take a look at what these numbers actually are. So looks like I visited here before. All right. So these are different number systems. We're just concerned with the left-hand column and the right-hand column. And right here we can see that 65 is indeed A. But if I add 26, I get 91. If I go down to 91, so here's Z is 90. 91, it isn't a lowercase a. We've got the open square brace, the backslash, close square brace, the caret, underscore, backtick, and then finally here we get a lowercase a. 97. Help me with the bits for 97. 64, 32, and 1. Let's try another one. Let's try I think I'm going to pick on the letter J today. J is 74. All right, help me out with the bits.
64.
Oh, like that. Okay. And then if I look at lowercase j, that's going to be 106. So let me do this. 106. 64, 32. One thing that there's a significance to going from uppercase to lowercase letters. If I go to google.com and I type APPLE, it brings us immediately to obviously the most famous Apple. And note that the case is different. So computers are dumb, and the way they like to match is with exact matches. So there has to be a process. There was a process that was gone through to get from my funky case here to right here. And the way to do that is to take my search string and convert it all to lowercase, or convert it all to uppercase, doesn't matter, one or the other. And then everything on the web that Google is indexing, they're converting it all to uppercase or all to lowercase. So now we can do exact matches, right? Just see if what I entered equals what's out there on the web. And the question is then, well, if I'm going to make everything uppercase or everything lowercase, what is the conversion that has to occur regardless of the string I type in? So what is the difference between upper and lowercase when you compare these two?
32.
The 32-bit. I mean, so that is the reason why it isn't 26 after. It's 32 after, because in order to go from lowercase to uppercase, you just flip one bit. And that's very easy and very efficient for a computer to do. Right? Why the 32-bit? Why not 16-bit?
Well, there's 26 letters, so you need to have it.
Right. So if I take 65 and I add 16, that gives me 81, and 81 is, of course, still part way through the uppercase letters. So the reason the 32-bit was chosen is that it is the lowest valued bit that is greater than 26. So that's their logic behind that. All right. Help me, let's move along to a slightly different topic. I want to create a vector of floating point numbers. What is that? Help me out with that. I need this up here. Anyone remember enough to give me a line of code to create a vector variable of floating point numbers? I'll give you a hint. Here's my hint. All right, you finish.
Give vector a name.
We'll call this floaty.
And then
So,
sign.
I think you're on the right track. So the thing with vector, so vector is in the standard library, specifically the standard template library. Templates are a syntactic construct that lets us create kind of generic algorithms where the only difference between the algorithms is the kind of thing. So vector, we can look at a vector generically as a list. You know, a list of strings, a list of floats, a list of characters, list of integers, list of dates, list of nights. All right, and the only difference between them is the kind. Otherwise, the way you store them is exactly the same, or the way you sort them is the same. The way you get the third one is the same. So that's the idea of a template, is the algorithm, the behavior is the same regardless of the kind of thing, and the only thing different is what kind you're talking about. So they have this syntax, which you just have to commit to memory, basically, which is inside of the angle braces, after the kind of thing, a vector, you have to say what it's a vector of, and then the variable. What is the member function that the vector has for adding an item to the vector? Pushback. And I guess we can have another 0 in there. Yeah, so I can go ahead and do that. What if I want to print them all out? Let me add a few more here. I won't be satisfied. I heard a for loop. All right, for.
I is less than floating top length.
In this case, I don't think a vector has length. Hey, let's try it. I'm almost positive that it does not have length. But, let me actually try compiling it at this point. Oops, what did I call this? Thank you. You're right. What's the alternative? Half? Oh, that would be for accessing an individual item in the vector. What if I need to know how many items are in the vector? There you go. And this is the same. So you not only have you not only have vectors, you have lists, you have maps. There are a whole bunch of different ways of storing a bag of items, essentially. And every one of those containers has a function called size. So that's one thing that you'll enjoy as you learn more and more containers in the standard template library, is they have a lot of functions that are the same. So let's say cout. Let me put floaty square brace I square brace equals so I'm going to print out each of those. It's complaining about line 34. It doesn't know what I is, but it didn't complain about line 33. It knew what I was on line 33. What's going on? All right. Also, a way of getting a hint on that, if you're kind of staring at it and not sure, is if you recall in Vim, the gg equals g is going to reformat your code, and the reformatting does see what you don't see necessarily, what you may not see. gg equal, whoops, hang on, not in insert mode, obviously. When I look down there, when it reformats it, it actually outdents this one to be at the same level of the 4 because it knows that it's not part of the loop. So that should give you a visual cue that something's amiss. The moment I throw in the curly braces, if I do gg equals g again, then you'll note that it went ahead and indented it. So let's go ahead and have a go with that. That's all right. I think one of the things that makes it look a little bit kludgy is that our output isn't lined up nicely once we hit the 2-digit indices. So let's add a little bit of code to make that look prettier. There are what are called manipulators. They manipulate the output stream, or they could manipulate the input stream depending on what it is. So you can include, and this was in some code that I had in one of the labs, I believe, iomanip. So that allows us to use all the input and output stream manipulators. And the manipulator that's very nice in this case is called setWidth. And that manipulator is manipulating the following thing to print out. So I will print out in a field that is too wide. So let's go ahead and compile that and take a look at that. Now we can see it's all lined up nicely. Maybe you don't like the way it looks there, and actually, before I go into that, let me just say that this width can be anything you want, right? We can make it 5. In this case, maybe since the indices are numbers, we'd like to pad it with zeros. So let me go back to 2 for a minute. And there is something called setFill, which is what do you want to fill in everything with. If you have a field that is greater than the thing printing in the field, then what do you want to fill in the additional space with? In this case, we'll fill it up with zeros. Let's try that. Note that I set the width back to 2. Doesn't have to be 0. It can be an uppercase Q. And of course it doesn't have to be 2, it can be 5. But Q is odd for that, so I'll put it back to a 0. I'll leave it as width 5 just for the sake of the notes. What about strings? So I'm going to create a string called name, and then I will create a get line. And I want to, from the keyboard, I want to fill up name with information. Now I want to loop through it for int I equals 0, I is less than name. And here size works nicely, but length was actually proposed originally. Nicely, this string class has a member function called length, which is actually identical to the member function size. It's just when we're dealing with strings, we're thinking in terms of words as speakers of English, saying the word has a length of, or the string has a length of, is just rolls off the tongue better than calling it size. So that's the only reason why length is provided. It's just synonymous with size, so you use whatever turns you on, I guess. So let me see. Let me actually steal this code. I'll say lines 34 through 37 yank. I will paste it here. And let me just change some words. It's no longer floaty, it's name. That's name. Now it's waiting because it wants me to put in a name. Maybe I go with, let me go with the more sane width of 2. Oops. So that's how we can iterate through strings. There's actually a different way of iterating through strings and vectors and in general lists of things. This comes from this kind of for loop actually right here, for where you have an initializer, a truth condition, and then something that occurs at the end of the loop. This loop has existed since probably the 70s, I guess. A lot of the stuff that we've been doing has been around that long. The C++ specific stuff like classes came a little bit later. But in 2011, where we are compiling with this text right here, this std equals C++11, so what we're invoking is a relatively recent standard. We could actually, incidentally, there's 2014, there's a 2014 standard, there's even a 2017 standard. If you wanted to go with 2017 and kind of have the latest and greatest, you could. These various standards get, I guess, more and more modest as to the new features that are thrown in there. But 11 was sweeping. There basically hadn't been any standard prior. For 20 years there hadn't been significant progress in C++, and they finally rolled out something with some new and exciting things. One of them is a new kind of loop. So let me take this example here with floaty, and the syntax, it uses the word for. That's the syntax of it. So there are just two things here, one of them and all of them. So I can say for, and we've got something there. All of them would be floaty here, which is, right, our vector. So that's what I'm reusing as our vector. One of them. What kind of thing is one of them? I have a vector of what? Float. So one of them is a float. Float. Give it a name. I guess I'll call it FL. Doesn't matter. Whatever you want. Yeah, and so let me make that a comment, and let me say cout using new C++11 standard loop. Add a quote, a new line of quote. Have some errors there. There we go, a dot out. And then we can see right here a nice easy way of iterating through lists of things. That'll work with strings as well. You can get through each character of a string that way if you want. There's another way of iterating through vectors and other things from the standard template library, and even you can iterate through strings this way, but it throws people for a loop, and it's using something called iterators. So the idea is that your vector is just sitting out there with 20 or 30 things in it, and if you want to go through it, you would use something called an iterator, which is nothing but kind of a pointer pointing to one part of it. So you want to start with your iterator at the first item, and then you have your iterator increase by 1, and so now it's pointing at the next item, that kind of thing. The syntax for it is absolutely horrendous. So what I have to do, and I'm going somewhere with this, you have a vector of floats, and what I want is an iterator. That is the kind of thing it is. So just like I say int I equals 0, excuse me, that isn't what you say at all, is it? For int I equals 0, I is less than, right, that kind of thing. So this is, instead of int, this is the kind of thing I have. I'll call it iter. Let me zoom in here. What is it equal to? It's equal to our vector floaty dot begin. So that initializes our iterator with the beginning of it. Then we can say iter does not equal floaty dot, anyone want to guess? I want to loop until we reach the end. Plus plus iter. And then I can just say, the syntax looks a little bit funky. Using iterators. I don't want you to get hung up on iterators at this point. I'm just using it as a way of introducing something else that's kind of nice. So actually, maybe I'll make this a cout statement. Cout using iterators. And I'll put a bunch of equal signs so that it really stands out to our eyeball. You'll understand what I mean when you see it run. Ichabod Crane. And using iterators, right? So that worked. That's yet another way. This is painful. And it gets a lot worse. You can have iterators of iterators inside of classes, and this thing can literally become 60, 80, 150 characters to type out the kind of thing it is. And frankly, it becomes a chore for, I mean, even a seasoned programmer who's been doing it for years. It becomes a chore to figure out exactly what that type is. So there's a keyword that was repurposed in the 2011 standard to make things easier. And that keyword is auto. And I say repurposed because auto is a variable that actually existed in the original C language, but it was never ever used. And the reason it was never ever used is if we go all the way back to, I don't know, what, the second week of class when we created variables. In the C language, if you wanted to create a character, you'd do this, but you could also do this. Auto. And that obviously is short for automobile. No, it's short for automatic. And the reason, the rationale between calling it automatic is it is a variable that is automatically created on line 9 and line 11, and then it goes out of scope at the closing curly brace, right? But the deal is, well, why is anyone going to waste time typing AUTO when you can just do that and it means the exact same thing? So it was a keyword that was never used, literally never used. And so they repurposed it in 2011, and what they said was, let's use that keyword to have the compiler automatically figure out what kind of variable it is. So I'm going to comment that out, and now I can take all of this and I can say, you figure out what the type is. You figure out what iter should be. And it can. The compiler can figure it out because the compiler knows what this is. It knows that the begin function is going to return, the begin function of floaty is going to return an iterator to a vector of floats. So the compiler can figure it out just fine, and it makes it easier for us as programmers. You don't have to use it only in this context. Let me give you another example. Auto ch2 equals the letter B. Compiler can work with that. Why? Because the compiler knows what kind of thing the character B is, so it knows that ch2 must be a character. Oops. And sure enough, it compiles, and I won't run. The running is just going to be what we've seen before. So the idea of ASCII values and with characters and iterating through strings, those are what comprise the two labs this week. I think with this stuff that we talked about here, that you should have the lab well in hand, both labs. I seriously think you could probably knock out both labs today. Any questions about anything or curiosities? Doesn't have to be on what I'm talking about. Yeah.
With the ASCII, why was it going to use the base 2 for the two
For the when we were looking at the binary stuff.
Yeah, was it because it was binary that
We use base 2 because of the computer's natural affinity for semantically internally it's storing things as switches, right? It's either on or off, and what that would represent is an electrical charge at some level. Either the charge is present or absent. For things like your thumb drive, which obviously you unplug, then it's using like magnetism for some bit physical, I don't want to call it a bit, some physical portion of that medium is going to be charged versus uncharged or versus a reverse charge. I'm not a hardware guy, I don't know, it's all magic to me, right? But it's something like that. So yeah, so that's why it's base 2. Hexadecimal, so there are other systems that you commonly see. The two most common ones that you see when you're working with computers are octal and hexadecimal. And the reason is for it being very natural to represent binary numbers in those other systems. For example, hexadecimal, as the word hex implies, is that it's base 16. So in hexadecimal, you have 0 through 9, and then you have, that takes care of 10 of them. You need 6 more, so A through F, A, B, C, D, E, F, yeah, it covers the next 6. So 0 through 9 is exactly as we know 0 through 9 in our system. A would be 10, and then F would be 15. And the reason that works really nicely is, let me take my bits here. In hexadecimal, let me see, hexadecimal, let me say hexadecimal, what is an F equal to? Not the character F, we're not going to an ASCII chart, but in base 16 hexadecimal, what is an F? An F is 15, right? Which bits do you have to turn on for 15? 8, 4, 2, and 1. And there are 8 bits in a byte. So that means that any byte in the computer we can represent as 2 hexadecimal digits. That's why hexadecimal is so popular in computers, because just 2 of these characters nicely represents an entire byte. In fact, if you come here, you'll note that one of the columns here is hexadecimal. So the uppercase A is hexadecimal 41. How do they come up with 41? We do the exact same thing. We've got this ends up being 16 to the 1. This is 16 0. This is 16 squared. and this is 16 to the third, and so on and so forth. What was the number? It was 41. 1. If I come over here, bring up a calculator, what is 4 times 16? That's 64. And then plus 1 equals 65, which is equal to our letter A. All right. So 2 digits work very nicely for 1 byte. 2 hexadecimal digits. Any other questions? All right, then I'll cut you loose and we'll see you in lab.